Okay, then we are recorded. None of you is seen here. I will not tailor towards the online participation, so I won't repeat your question because I think the online participants will not be able to hear you, but that's okay. Welcome everyone. Thank you for coming so early in the morning. If you're like me, you don't like to wake up so early in the morning. Usually that would be the first lecture where I get to know you a little bit, and I was sick. I'm a little bit, you can hear this voice is not fully recovered yet, so I'll try to keep it down. Let me start with telling you a little bit about myself. I studied mathematics in Berlin, and then I did my PhD in theoretical computer science. I lived in lots of different countries doing postdocs, either in computer science or in mathematics. And now I'm here in the assistant professor in the computer science department. But my research area is really in between mathematics and computer science. So for instance, recently I applied for a grant, and the committee, they first put me in the computer science committee to evaluate me, and then they put me in the mathematics committee to evaluate me. And my research area is really in between. I think and discrete mathematics is traditionally in between mathematics and computer science. So I think it's also a good fit. What can I say about myself? I'm usually not that often sick, especially since the pandemic. I never get sick, and now it's worse timing. I like Lindy Hop dancing. If anyone is doing this, anyone's doing Lindy Hop dancing? Okay. Otherwise, I like bouldering, but I'm not doing that too much, more with colleagues after work. I used to juggle a lot. I used to play basketball when I was your age. What else? I guess. Otherwise, ik praat ook een beetje Nederlands, maar ik wil het college niet in Nederlands geven, omdat ik maak heel veel fouten en dan denk je dat ik heel stom ben. En ook dan moet je altijd voor mij wachten, omdat ik dat misschien niet begrijp. En dan moet je de tweede keer uitleggen. Dus het is eigenlijk makkelijker voor mij mit Engels. Ich kann auch Deutsch reden, wenn ihr das auf Deutsch haben wollt, dann ist es für mich eigentlich die einfachste Sprache, obwohl ich viele Begriffe auch nicht auf Deutsch kenne. Okay, I think that was a little bit about myself. Yes, and maybe we get to know each other in the course of the next 10 weeks a little bit better. Then homework assignment 1. So that's a bummer. So I don't really know what happened, but apparently I uploaded the solution instead of the homework. How many of you have seen the solution? Aha, so apparently this was just, apparently I was notified quite quickly, yeah. So then it's maybe not such a big issue. Interesting. Yesterday I was thinking with colleagues on what to do, but if almost none of you have seen the solution, then maybe it's not a big deal. Okay. So you're not even aware of that? Okay, I was under the impression that the solution was there up for 5 days. Yes? I downloaded it. Yes? Interesting. Okay, that's good news. I don't know what happened there. So apparently one of your fellow students was very quick in telling me, oh, there's a solution online, and yeah. Okay, then I think we can go through. It's good that I wanted to say yesterday, okay, this assignment is for 0 points, but if none of you saw the solution, then that should be fine. But I guess 1 or 2 students will have seen the solution. Do you mind that, or? Okay. Okay, then, we are saved. Very good. Okay. Let's cross this out and say, I don't know if that's, yeah. So I asked you to fill out this questionnaire. And usually I get lots of interesting things when I see this questionnaire. Students having very like assumptions about courses that I teach that are very incorrect. And then at the end of the course, they say, oh, I thought this, and that didn't happen. So that's why I do this intake at the very beginning. But in this case, I didn't see anything wild. So for instance, I was teaching a course, AI for Game Technology. It was supposed to be able to program in Python. Students were not capable of programming Python, and at the end of the course, they said, yes, you should have given more support to teach us Python. And then what I did the year after, I told them in the intake, you're aware that if you can't program in Python, you need to learn this yourself. No one complained in Caravan. So that's the purpose of the intake. The only thing that I read is that one student said he would like to learn more about probability theory and statistics. And I think this is often where discrete mathematics is seen, that you have to, you know, compute some probability, and then you count the good, you count the all, and then you take the ratio, and then you like, now we did probability theory, but really what you did is combinatorics. But we will not really cover probability theory. But otherwise, I saw that most of you are highly motivated, so that's very good. I mean, few are really, really motivated, but you know, you're in the positive part, so that's good. Some of you are not really sure if you satisfy the prerequisites. So there are some people like, yeah, sure, I can do it. But there's like a few people who are like, I'm not really sure. So homework sheet 1 should answer this question to you. Yeah. Have you looked already at homework sheet 1? And who thinks it's doable? Okay, that's good. But you also made it to the lecture. I don't know what the people who don't make it to the lecture. Yeah, I think that was it about the intake. So there were some people maybe saying, okay, they like to be very free, and I like also to give students freedom, because for me, what I always think is, I want to teach something. What do I need to teach that? For instance, I want you to teach content about discrete mathematics. I hope I'm good at explaining it, but you can also read it. Some people prefer to read it, you can read it. So no need that I ask you, you have to come, right? But I also want you to speak to each other, and that I want that you give each other feedback, because this is something, a very important skill to learn that I also want to teach you. Well, for this, I need you to come. So that's why these tutorials are kind of semi-mandatory, because we have this in-class assignment. You can skip them, you lose some points, you can still pass the course with a high grade. Not really sure it's worth it. So that was maybe also a question from the intake. Any other questions regarding the organization of the course now that we're here in real life? Anything that you're particularly upset about, or now is the time to mention it? Okay, good. What about you? So it would be nice that I get to know you also a little bit. So maybe let's start with some easy questions. So who of you lives in Utrecht? So that's like more than half. Oh, but that's the people who are here, right? Maybe the people are not in Utrecht there. Let's say the city. Did you answer for the city? Okay, who's living in the city of Utrecht? Okay, that's few. Who lives in the, not in the city, in the province? Okay, so that's like Zeist, Bunnik. Who lives, like, who has more than 1 hour commute? Okay, less than an hour commute? Okay, so who of you studies computer science? That's okay. That's like half. And who studies mathematics? That's the other half. Who's studying neither? Okay, so one person who studies neither. So I thought that so last year, I think what happened is a majority of the students were mathematics students. And what happened then is, yeah, this course is a computer science course. So mathematics, like, yeah, we can just teach it ourselves. And so now what I try to do is I really make this course accessible also for computer science students. And when I say this, it always sounds like computer science students are not as good. But I think they just have less mathematical experience, right? So if you are a runner and you run every day and then obviously you're faster than someone who doesn't run, right? And no one would question this. But then sometimes we mix up experience with like, oh, this is like a smart or not smart person. But when I say, computer science, I always mean they're less experienced. So for instance, Lucas, he studied computer science, but yeah, I mean, you see his mathematical abilities are tremendous. Like he is not 1 year in his PhD, he already wrote 3 papers by himself. So yeah, really impressive person. So I don't want to take these things mixed up. So who of you is Dutch? Okay, so who of you is not Dutch? Okay, so we're 2 people, so okay. But you said your name is Martin? But that's a Dutch name, no? Okay. Okay, Martin is, yeah, then we could have spoken German. But I think the rest of us okay, should we get started? Did you read up what I asked you to? Okay. Yeah, so one of the things is I don't really know how fast I can go. So maybe at the end of the lecture you can tell me this was too fast or this was too slow, and I can adjust. Okay, so section 2.4, large implies tall or wide. So let's say P is a poset, ground set X, and this order here, and we call a set A subset X independent if there is no XY element A X smaller y. Okay, there's, I guess, a small subtlety here that I do incorrectly. By the way, you don't have to take notes, everything in the book, right? Except, you can, of course. I guess if they're not equal. Because of reflexivity, if they are the same, then B. So, and it's also called an anti-chain. And we say two elements x, y are comparable if x smaller y or y smaller x. Good morning. And otherwise they're incomparable. And then we say alpha of P is the max of A independent. And that's also called the width. And yeah, then we now have to define the height. And we say C is a chain if all x, y are comparable. So an anti-chain is no one is comparable, a chain is everyone is comparable. And then the width, oh, sorry, now the height, which strangely is abbreviated with omega. So it's not a W, I think it's an omega. Is the maximum C is a chain. Yes, and that's the height. So you may wonder why we have this alpha for width and omega for height. I think this has to do with graph theory, where these notions also exist. And then there's a tradition there to use alpha for independent sets and omega for clicks, but we can come to this later. Okay, these were only some definitions. And then we have the theorem. Which says alpha p times omega p larger or equal to the size of x.
Unless I'm misreading it, the definition of independence now says that the elements in A have a relation. Maybe I'm just not seeing it correctly.
Oh, for all x that are x and y that are not equal?
Yeah.
Oh yeah.
Yeah.
Oh yes, yes, yes. Okay, so let's prove that theorem here. So I prove it by picture, but the picture will help. So I cooked up this little post set here. Okay, so that's my post set. Should hold for any post set. So I define now some. I partition this post set. You can draw a different post set. You don't have to take mine. Yes. No, not the value is independent. The set is independent. The set is independent if no two are comparable. So maybe what this says is that either this post set is relatively tall or this post set is relatively wide in an intuitive way. When you draw it, I think we already had Hasse diagram in the part before, right? So yeah, I drew here the Hasse diagram. Do you remember the Hasse diagram? No? It's just I don't draw all relations, but I only draw the relations between immediate predecessors and successors. So for instance, there's an edge from here to there and an edge from here to there. This means this guy is smaller than that guy, but I don't draw all of them. I just draw to the immediate successor. Okay, so now I take all the minima and I call this x0. And then I remove them. And all the minima form an independent set, right? Because if two minima would be comparable, then one of them wouldn't be a minima, because then one of them would be smaller. And then what I do is I remove them, and then I do the same again, and get the next set of minima. And the next set of minima, and the last set of minima. So, yes?
Right at the there's like direct connection from x0 to the upper right. For the bottom right point?
This one here?
Yeah,
So you would put it in x1?
I think so. Oh, sorry, no, I'm just wrong.
Yeah, that's why I try to be a little bit tricky here. So, but it's a good thing that you point this out. So this one looks like it could be in x1, and the reason is because it has a direct predecessor in x0. But really what happens is that it's not a minima once we remove x0 because this guy is smaller. Yes? Yes, it should. Oh yeah, I forgot an edge. Very good. So, so there are a few points that we need to see now, but you will agree with them, I think. So this x0 up to xk is a partition. That's clear by definition, right? Then xi is independent. And then the third one is that the height of this poset is at least k. And that's the most difficult part. But you will see it's not too difficult. So we start with, we now need to construct a chain, right? Length t of length k. Do you see how these three things imply the claim? Right, if each of the x0 is smaller then, so let's say each of the x0 is alpha I, then if we don't have this, if we have then, how do I do this? So it's a partition, and each of the x0 is at most alpha I. Now, if I find a chain here of that length, well, I guess maybe I can argue differently. If I have x divided by k, then this is a lower bound on WP, or wait, on the height is WP, yes. Oh, this is on alpha P, and K is the lower bound on this, and so we get the equation. Okay, so now I need to show that there is a chain of length at least k. Why did I call this x0? I think it makes more sense to call it x1. Sorry. Any idea how we get this chain? So we start here and pick any element in x3. So we know x3 is not empty, right? Yes? Sorry, okay. Yeah, sorry, I had bad naming. Yes?
Yeah, I thought I was going to be with questions.
Okay, do you have so I want to construct a chain, I start here. Yes.
The elements already have to know that
So,
element is minimum one.
so we know x4 was not a minima before, so there needs to be someone who's below him, and now we could think, oh, but maybe there's a guy only in x. We want to pick someone in x3, right? And why is there someone in x3 below this element? Because otherwise it would have been, that guy would have been a minima when we look at all the minima before. That's the key argument. And then we can repeat that. And then we find a chain of length k. So let me repeat. We start with the top. And we want to find a chain, and we always want to find someone one set below. So if this guy didn't have a predecessor one below, then it would have been a minima when we looked at those guys. So there must have been someone smaller than him, and that must be in the set. And this continues. Yeah, one thing I noticed, what is maybe one advantage of a lecture over a book, the book gives the same argument, but it needs much more notation because it can't like explain things with words so much. Now we go to Erdős-Sekeres. So maybe I should say that I lived for 2 years in Hungary, and for those who know a little bit Hungarian, these are very Hungarian names. Erdős is the person with the second largest number of publications of a mathematician ever. You know who is the one mathematician with the largest number of publications? He's not a mathematician. No, but he's German. Or actually, is he German? Maybe not. German speaking. He was in Germany for some time. Some mathematician you heard many times in your life is not Pythagoras. Yes. Very good, Euler. So Erdős just follows up on Euler, where Euler had the advantage he didn't have to go through the peer review process. It was when he published, he just like a blog post, right? This is like. But Erdős is a person with the second largest number of publications, and he died, I think, 10 or 20 years ago, so not so recent. But let's go to the theorem. So we have capital N equals n squared plus 1. So, and we have a sequence of these numbers. So we think of these numbers as ordered, maybe. So the indices actually matter. And then Erdős-Sekeres says there is a monotone subsequence of length n plus 1. So first, what does monotone mean? Monotone mean either it keeps increasing or it keeps decreasing. So it goes up or goes down. And then subsequence. So if you have some elements, right, then that's a subsequence. Just take a subset of them in the right order. So this is x1, x2, x3, x7, then x2, x3, x6 would be a subsequence. So in the homework assignment, there will be, you would you will be, for next week, you will be asked to figure out a second proof for Edish checkers. Lucas didn't like that proof so much, so he's like, okay, let's give an alternative proof. Yeah, I think it's sometimes a little bit difficult to see the beauty of it, but actually I think there is a very nice proof. So we define some order on xi, xj. So we say xi smaller than xj if and only if I is smaller than j, and xi smaller or equal to xj. And then what we have to observe is that monotone increasing sequence, so an increasing sequence in this order corresponds to what is it? Increasing is comparable, so that means to a chain. And now a decreasing sequence, a little bit more difficult, but there we see that it's an anti-chain. Right, if you look at this, those two are not comparable because the index goes up, but the value goes down. And that's true for any two, so it must be decreasing. That's a little bit more tricky to see. And yeah, and then we just apply this previous theorem here. Yeah, so you can do it if you could do it by contradiction if you're lazy like me, and then you say if both alpha. So do you use this symbol like a lightning bolt? Yes, some say yes. Who knows the symbol? Half. Okay, okay. So this symbol means I want to have a contradiction, a proof by contradiction. So I write something that's wrong in order to derive to something that's wrong as well, and then I know what I wrote was wrong. So let's say alpha is at most n, and omega is at most n, and that would lead to capital N is at most n squared, and that would be a contradiction. And so we have the proof. Okay, yes?
What was the square
so it stays for a tombstone, or now we can bury this problem and don't have to think about it anymore. But it's a common practice in mathematics to finish your proofs with a little square. But you can also use hearts or just stop. Yeah. But I think it's also from Erdős to introduce this tombstone. That's yeah, mathematically folklore, so to say. Other questions? Okay. Let's go to chapter 3 then, combinatorial counting. So combinatorial counting is just the question: how many ways can we do something, or how many are there of something? And I guess that's a big topic altogether in discrete mathematics, and it has applications to various other areas. For instance, in probability theory, we want to know probabilities, so we count certain sets, and then we can take ratios and then we know probabilities. But maybe where it's interesting for computer scientists is we want to know how fast an algorithm is. So we want to count the steps. And the steps often go through certain combinatorial things, maybe certain subproblems that we need to go through. And then we want to know how many are there of those. And then this tells us how fast that algorithm is. So that's why combinatorial counting is really useful for people in algorithms. Okay, so let's start with some easy things here. And I will fear that many of you are familiar with something that I tell you for the rest of the lecture, but I just think that it comes up in so many other areas, and maybe you even have it in school, but I don't want to skip it. Okay, so easy theorem, or easy proposition. We have functions from x to y. We want to know how many functions there are, and x has size n and y has size m. Easy proof by induction on n. So we have n equals 0, and then m to the 0 equals 1. Is there a function? Yeah, I guess there's one function, which is a little bit silly, but nothing gets mapped to y. This is a one function that there exists, which is one of these, how do you call this, pathological cases that we still define just to have the induction basis with n equals 0. But you can also have induction basis with n equals 1 if you don't like n equals 0. So then you would have one element here and m here. And then you have indeed m choices on where to map this one element. Okay, so now we go with the induction step from n to n plus 1. I didn't draw a picture for that. Oh, that's the next proof. Okay. So we have here x and we have y. This here has, let's say, size n plus 1. So we have to map all of those guys here somehow. And by induction, there are m to the n many possibilities for that. And then for this guy, there are m possibilities. So in total, we get n times m to the n equals m to the n plus 1. Okay, I guess this is not really that interesting, but maybe a good way to practice induction. Okay. Question to this? So number of subsets of x is 2 to the size of x. I guess you can prove this by induction. Maybe let's skip the proof by induction. We have a second proof here, which maybe is a little bit nicer. Is it okay to skip the proof by induction? Okay, maybe we only need one proof here. So we have this set A, sorry, that's set X. And if we have some subset A, we can build a characteristic function, which is 1 for X element A and 0 for X not element A. I finish this proof and then we have a break. So yeah, so what we do is we show a bijection between number of subsets of X and functions from X to 0. How many functions are there from X to 0, 1? Using the proposition we just proven. What is M here in that case? Yes, very good. See that? This set has size 2. So here this number is 2 to the n, this we already know. And now we have to show this bijection. And now for each a, we map it to this function fa. And what we have to show is that this function is a bijection. So what properties do we have to show? One-to-one and onto, yes. So I have to say I use the terms injective and surjective because this is what I learned when I was your age. But that's the terms that the book uses, so you're very good. 1-to-1 or 1-to. So okay, 1-to-1. If we have two different sets, we get two different functions, no? And then let's take any function here, then it maps some elements to 1 and some to 0. All of those that map to 1 give us our subset. So should I repeat this? So let's say we have this function, so some other function f, right? Or let's call it g, so not to confuse anyone. So let's say we have this function g, then we can ask, what is the preset of 1, and that set we call b. And then it turns out that f, the characteristic function on the set b, is the same as g. So now we found under this phi here, this phi which describes this bijection, we found the pre-image of an arbitrary function g. Okay, with this, let's have 15-minute breaks and then we continue.